So let's do a couple examples before we actually look at an algorithm. So, at the beginning of talking about divide and conquer, I mentioned this thing called binary search. So how does binary search work? Well, it searches an array, a sorted array, by determining which half of the array the element that it's trying to find is in, and then going and searching that half of the array. And it just keeps doing that recursively until it's done, until it finds the thing or determines that the place where it is, where it should be, it is not, right? So it either finds it or determines that it's not there, and it gives us the recurrence relation T of n equals T of n over 2 plus 1. Now, I'll mention that the Levitin book makes, I think, an uninteresting distinction between a divide and conquer algorithm and what they call a decrease and conquer algorithm. And so they classify binary search as a decrease and conquer algorithm. I think the distinction is not that important, so I'm classifying it here as divide and conquer. But if you're looking for binary search in the Levitin book, you actually won't find it in the divide and conquer chapter. So there's your help for looking for binary search. All right, so let's think about what this is. So we can rewrite this in terms of the master theorem recurrence relation. So the master theorem recurrence relation has a coefficient in front of the t. What's that coefficient? Well, it's just 1. So it's 1 times t of n over 2 plus, and then we need to write 1 as a function of n. How do you do that? Well, that's just n to the 0, right? So this is 1 times t of n over 2 plus n to the 0. Okay, and so a is 1, b is 2, and f of n is n to the 0. Right, so this piece here is our f of n. And so how does this work? Well, there's a couple ways of thinking about it. The way that it's presented in the theorem that I presented in this series of lectures, in lecture 9, is I say, let me think about the critical exponent. So what is my c? Well, my c is log base b of a. And so c here is log base b of a. So what is that? Log base 2 of 1. What's the logarithm of 1? Well, in any base, it's 0. So my critical exponent is 0, which, if I'm trying to understand whether f of n is growing faster than n to the c or slower than n to the c, I see that it's growing exactly the same speed as n to the c. Okay, so this is a slightly more advanced way of thinking about it. A simpler way of thinking about it is just to take a look at this expression. So let's think of this as d. So let's call the exponent that f of n has d. And then let's compare b to the d with a. Right? So what is b to the d? B to the d is 2 to the power of 0, which is 1, which happens to equal a. So it turns out if b to the d equals a, right, here what do we have? We have b to the d equals a. Then this is exactly the balanced case. Balanced. And so the approach here where we think about, rather than thinking specifically about the critical exponent, which can be kind of hard to evaluate in your head sometimes, and rather thinking about, comparing b to the d with a, this particular formulation and approach to the master theorem is what the Levitin book uses. So if you go look up the master theorem in the Levitin book, they'll split apart the cases like this. And they'll say, hey, think about f of n as a polynomial, find its degree, right? Find d, the degree of f of n, and then compare that with b to the d. Or compare b to that power with a. And it's exactly equivalent to the method that I showed in the videos earlier, but it can be slightly easier to think about. So if b to the d equals a, what do we have? We have the balanced case, and so that means that t of n is big theta of log, and if I'm very, very precise, I can include the base, but it doesn't matter too much. Log base b of n, which is just big theta of log n. And if I want to be very precise about it, I can say log base 2 of n. Okay. So there's binary search. I also talked about this max find algorithm. So let's call this number 2, the max find. And so recall max find was this, it was this recursive algorithm where we would recurse on the lower half of an array and then recurse on the upper half of the array and go ask the recursion to get us the largest element. And then our base case would just be to return the bigger, or to return, you know, the element in a one element array. So it would recurse down, and then at each point as it bubbled up, it would compare two numbers. So max find had this recurrence relation, t of n equaled 2 times t of n over 2 plus 1. So I can think of that 1 as, again, as n to the 0, right? And then if I use the Levitin approach, I'll say, hey, a is 2, b is 2, d, the exponent here, right, that's d, d is 0. And so then I'll compare b to the power of d with a. So b to the power of d is 2 to the 0, which is 1. And 1 is less than 2, which is equal to a. Right, so I have the case where b to the d is less than a. And so let's think about what that means. You know, b to the d is kind of governed by the by the overhead, so that the larger d is, the bigger the overhead is, and the larger the thing on the left is. And so if b to the d is less than a, that means that we're in the recursion dominant case. So this is the recursion dominant case. Okay, so if the recursion is dominant, what does that tell us? Well, that tells us that we have that strange n to the power of log base b of a. So that means, you know, if the recursion is dominant, then t of n is in big theta of n to the log base b of a, which in this case works out to this very simple form, you know, where we have the log base 2 of 2, and that's just 1. Right, so that's just big theta of n, because log base 2 of 2 is 1, n to the 1 is just n. Okay, so there's a second actual algorithm that works. Just for completeness, let's look at just a handful of other recurrence relations that we can evaluate using the master theorem. So here's a third example. My third example is going to be this recurrence relation. And this isn't keyed to a particular algorithm. We'll do real algorithms in a moment, but this is it's just a recurrence relation, and the question is, does the master theorem give us the answer here? So the recurrence relation is t of n equals 17 t of n over 4, n over 4. Okay, so you can imagine we recurse 17 times for some reason. On problems that are a quarter the size of the original, and then my f of n term is n squared. Okay, so in the Levitin approach, I'll find a, b, and then the exponent associated with the overhead term. So I'll say a is 17, b is 4, d is 2, right? Remember, that's d. And then I'll compute b to the d. So b to the d, and then compare that with a. So b to the d is 2 to the power, oops, sorry, it's 4 to the power of 2, right? So 4 squared is 16, and that's just subtly less than 17, which is a. So again, we have a larger than b to the d, which means we're recursion dominant, right? So b to the d is less than a, so recursion dominant. Okay, and then that means our t of n is big theta of that strange expression, the strange polynomial. So n to the log base 4 of 17. Okay, and just for fun, what is this, right? What is log base 4 of 17? Well, it's very close to 2. Right? 4 squared is 16, And so it takes just a tiny bit larger exponent on 4 to give us 17. And that's what log is doing here. Right? So this is just faster than n squared, or just slower, sorry. Right? Just slower than n squared. The algorithm scales just a tiny bit worse than n squared. Okay, so it's n to the 2.1 or something like that. See if I have that. I don't have the exact number here, but you can look that up easily enough. Let's do one more. So our example number 4 will be t of n equals something relatively simple. So 4 times t of n over 3 plus now the square root of n squared plus 5. All right, so now we don't have a polynomial, right? We're not in the scenario where f of n equals a polynomial, but f of n is still a member of a polynomial complexity class. So what's a? Well, a is 4, b is 3, and if we're using the Levitin approach where we find the actual exponent associated with f of n, what is d? Well, this function here is big theta of n. And you should have learned how to show that on the first homework. But what we have here is an n squared underneath a square root, and those two cancel each other, right? So you should end up with a big theta of n for this expression here. So my d is 1, right? This is my f of n scales as n to the 1th power. All right, so what's b to the d? It's 3 to the 1, which is just 3, which is less than, let's say b to the d is 3 to the 1, okay, which is less than 4. And so once again, we are in this the recursion dominant case. So b to the d is less than a. And so once again, we have recursion dominates. And we have t of n is in big theta of n to the log base 3 of 4, which is just very tiny bit slower than linear, right? So there's a few examples to get you started, and then there will be more on the homework where you can think through exactly what these different cases look like.